welcome to my YouTube channel of subject Basic Electrical Engineering. In the previous few videos, you have seen a chapter AC circuits. So, in previous videos, you have seen analysis of AC series circuits. So that means resistor and inductor connected in series or resistor and capacitor connected in series. So in this video, we are going to study about what if resistor, inductor and capacitor, all three elements are connected in series. So basically the video is all about series RLC circuit. So to understand series RLC circuit, first we need a circuit having three components, that is a resistor, inductor and a capacitor. So let's draw first a series RLC circuit. So in this figure you can see that there is one resistor, inductor and capacitor connected in series, and the resistance is denoted by R, inductance is denoted by L and capacitance is denoted by C, and XL and XC are the inductive reactance and capacitive reactance respectively. So these three components are connected in series, and we have applied some AC voltage source to this series combination. So you can see that Vt is the instantaneous value of the AC voltage applied to this circuit, and due to this AC voltage, It is the instantaneous value of the current flowing through all these three elements. And we studied that in series connection, current flowing through each element will be same and the voltage across each element will be different. So you can see in this figure, VR is the voltage drop across resistor, VL is the voltage across inductor and VC is the voltage across capacitor. So here analysis of series RLC circuit means we need to find equation of It, that is the current. We have taken voltage as a reference again, and the equation of voltage is Vt is equals to Vm sin omega t. So this is taken as a reference. We need to find the equation of current It and the phase angle between voltage and current. So we need to draw a phasor diagram to find the equation of instantaneous current It. So here three elements are there. So that three elements are the resistor, inductor and capacitor, and the current flowing through these three elements is same. So basically we can take current as a reference to draw the vector diagram. So we have taken current as a reference. Now VR is the voltage across resistor and I is the current flowing through that resistor. So basically the voltage of resistor will be in phase with the current flowing through that resistor. So you can see this diagram. In this diagram we have taken current as a reference on x-axis and VR is the voltage across resistor is in the same phase as we have drawn the current. Now let's talk about the VL. VL is the voltage across inductor, and we know that in case of inductive circuit, if we are drawing separately three phasor diagrams, so only we are talking about the inductor. So in case of inductor, current lags behind the voltage by 90 degree. But if we have taken current as a reference, so we can say that voltage of inductor will lead the current by 90 degree. So you can see this diagram, current VR is in the same phase and VL is above that current by 90 degree. Now let's talk about the capacitor voltage VC. We know that in case of capacitor, capacitor voltage is lagging behind the current by 90 degree, because we heard that current in capacitor is leading from the voltage by 90 degree. But here we have taken current as a reference, so the voltage will be lagging behind the current by 90 degree. So it will be below side. So this is the complete phasor diagram of RLC series circuit, in which current is taken as a reference, VR is in the same phase, VL is leading by 90 degree and VC is lagging by 90 degree. So this VL and VC is 180 degree apart from each other. So basically they will be subtracted, because one vector is above the reference and another vector is below the reference. But which voltage is subtracted from which voltage is deciding upon the higher value of the voltage. So here we are considering two cases, and that two cases are the VL is greater than VC, means either the inductor voltage is greater than the capacitor voltage, or you can say that VL is less than VC, means capacitor voltage is more and inductor voltage is less. So let's understand the concept of these two cases. So here we have drawn the vector diagram for the both the cases. So if in the first case VL is greater than VC, so that means VC in downside will be small and VL on the upside will be having larger value. So VL minus VC will be done, and the resultant vector VL minus will be is in the upper side of that phasor diagram. So now basically we have a current as a reference, we are on the same phase as current, and VL minus VC is the resultant voltage of inductor and capacitor, and it is on the upper side of this phasor diagram. Now if we want to add these two voltages, that is the voltage across resistor and the equivalent voltage of inductor and capacitor, so we are using the parallelogram method. So by parallelogram method we obtain a diagonal, and this diagonal represents the applied voltage V. So V is the answer of this phasor addition of these three voltages. Now you can see that this voltage V is leading from the current, or you can say that current is lagging behind the voltage. So if you want to find the equation of current from this phasor diagram, then we can say that there is a triangle, and we can apply Pythagoras theorem to this voltage triangle. So in voltage triangle there is a VR, there is a VL minus VC, and there is a diagonal which is total voltage V. So we can apply Pythagoras as V is equals to under root VR square plus VL minus VC square. Now let's put the values of VR, VL and VC. So the value of VR is I into R, because V is equals to IR. So here it will be IR square. In plus in bracket it will be VL minus VC whole square. So it will be IXL minus IXC whole square. Now that I square will be make common out from that bracket, so the equation will be under root I square R square plus I square in bracket XL minus XC whole square. So if we are taking I square common from this both term, then it will be under root I square in bracket it will be R square plus XL minus XC whole square. If this I square is taken out from this square root, then it will be V is equals to I under root R square plus XL minus XC whole square. And we can say that according to Ohm's law, V is equals to IZ, where Z is the impedance of this series RLC circuit, and Z is equals to under root R square plus XL minus XC square. So this was all about the phasor diagram in case of VL greater than VC. Similarly, you can see this second figure. In this second figure, we have taken VC is greater than VL. So in case of VC is greater than VL, we have to do the subtraction of vectors like VC minus VL, and the resultant vector VC minus VL will be on the downside of that phasor diagram. So we have taken current as a reference, VR is in the same phase as current, and VC minus VL vector will be downside of that phasor diagram. So now we have three voltages, one is VR and the another two voltages are VC minus VL. So we need to add these two vectors, because VC minus VL is the resultant voltage of two inductor and capacitor both. So we are adding that two vectors by parallelogram method again, and the answer resultant vector diagonal of that parallelogram will give you the answer of the resultant voltage V. So here if again we are applying the Pythagoras theorem, then again it will be V is equals to under root VR square plus VC minus VL square. If we are putting the values of VR, VL and VC, then it will be IR whole square plus in bracket it will be IXC minus IXL whole square. If I square is taken out, then it will be under root I square in bracket it will be R square plus XC minus XL whole square. If I square is taken out from that under root, then it will be I under root R square plus XC minus XL whole square. So you can say that this V is equals to I into Z, and here in case of VL is less than VC, impedance is given by this formula under root R square plus XC minus XL square. So this was all about the phasor diagram in both the cases. Now let's understand what is the phase angle in both the cases. So if we are talking about the first case, then the angle represented by that phasor diagram in first case is given by phi. And we know that the resultant voltage was leading and current was lagging. So if you want to find that angle phi, then we can apply tan phi in that triangle. So tan phi is equals to opposite side to the adjacent side. So opposite side was VL minus VC and adjacent side was VR. So if we are putting the value of VR, VL and VC, then it will be IXL minus IXC upon IR. So if II is cancelled out, then tan phi is given by this formula XL minus XC upon R. So you can find the angle by this formula. Phi is equals to tan inverse XL minus XC upon R. Also you can find directly power factor cos phi from that triangle, and that is nothing but R by Z, because cos phi is equals to VR by V. VR is IR and V is IZ. So II will be cancelled out. So you can directly find the cos phi, that is power factor, that is R by Z. Remember in previous both video, in case of series RL circuit and series RC circuit, power factor was the same, that is R by Z. But the difference is that impedance in different circuits will be different. So this was all about the power factor angle. Now if we want to write down the equation of current in this series RLC circuit in first case, then we can write the equation of voltage as V is equals to Vm sin omega t, and equation of current is written as I is equals to Im sin omega t minus phi. In that phasor diagram, you have seen that voltage was leading and current was lagging by angle phi. So if current is lagging, then you have to put negative angle. Then the negative angle is minus phi. So now let's talk about case number 2. And case 2 is, in this case we have taken VC greater than VL, or you can say that VL is less than VC. So in this case our angle, resultant angle was downside. So you can say that in this case current is leading and voltage is lagging, and obviously in this case capacitor is having larger effect, and we know that in case of any capacitive circuit current always leads. So now let's derive the phase angle from this vector diagram. So you can see that phi is the phase angle between voltage and current. So if we are applying tan phi to this triangle, then tan phi will be equal to opposite side to the adjacent side, and opposite side is nothing but VC minus VL and divided by VR is the adjacent side. Now let's put the values of VR, VL and VC into this equation, and it will be IXC minus IXL divided by IR. So if II is cancelled out, then the equation of tan phi will be XC minus XL upon R. So basically we got the same equation, just the reactance terms is interchanged. So if inductive effect is more, then it will be XL minus XC, and if capacitive effect is more, then it will be XC minus XL. So in this way you can find the angle phi is equals to tan inverse XC minus XL by R. If you want to find power factor directly from this phasor diagram, then cos phi is equals to VR upon V. And we know that VR is nothing but IR and V is nothing but IZ. So if II is cancelled out, so again the power factor cos phi is having the same equation as R by Z, where Z is nothing but the impedance of this side. So if we want to write the equation of current from this phasor diagram, then we can first write the reference voltage equation. And we know that the equation of the reference voltage was the V is equals to Vm sin omega t. And the equation of current I will be I is equals to Im sin omega t plus phi. Here in this diagram, angle is measured or mentioned in negative, but that doesn't mean we have to write negative angle in this equation. You look carefully, current is leading from the voltage. So you have to write the plus phi angle in this equation. So this was the equation of the current and voltage in both the cases. That is VL greater than VC and VC greater than VL. Thanks for watching this video. Stay tuned.